previous exposition, we talked about the differential equation and how it's very important and why I applied it into the LOSC curriculum with Regicalculus. And just to give a brief review on it, differential equations are very important because they model certain things in real life really well, or they rather give us constraints, or they tell us how a certain system evolves. So whether it be a pendulum, a spring, or a femboy with behavioral issues. So in today's video, or in today's exposition, we're going to be talking about the orbit. And this is not the regular orbit that I'm talking about, which involves, going around the planet or celestial body, not the type that's talked about in orbital mechanics or in rocketry or in physics. What we mean by orbit is a mapping between two groups, or rather, a mapping between a group and another group composed of transformations on a space, equipped with the binary operator. So I've already discussed in the previous video what a group is. So a group is a set N equipped with the binary operator dot or product, so such that all elements inside this set satisfy the group axioms. Try rewriting my camera. Okay. Or actually, I can just do that in editing. So today we're going to be talking about orbits, and I've alluded to what orbits are in my videos on applying group theory, improving the femboys RNK with the Stephenson-Maxwell paradox, and I used the Banach-Tarski paradox to prove that one set is another set, or rather a strong form of the Banach-Tarski paradox, that one set is another set, and I from there, with a stretch of logic, concluded that femboys are independent from the definition of being gay, which I formalized with the gay set, alright, or with the gay element. And so, yeah, it uses the concept of a group, and in the first exposition, I emphasized or corrected how I treated groups back then, and what actual groups are. So there's this thing that I mentioned in my episode on the Stephenson-Maxwell paradox, which I called, or which I mentioned to be the orbit. And what is an orbit in group theory? Well, as I said a while ago, the formal definition is a mapping between a group and another group. So yeah, that's the thing about it, a mapping. So what are maps? To first understand a map, I must first discuss to you guys what a function is. And you guys probably know this already. I've already discussed about functions a lot, and it's there on my Femboy Mathematics channel, where I think it was episode 3, wherein I discussed functional notation, their transforms and stuff. And functions are basically a machine. So they take some input x, so I will make a small machine here, and they spit an output y. So they take an input x, and then this is f of x, and they spit an output y. So given a coordinate axis or a number plane, let's say this is the real numbers, which I'll denote by r. Given a certain x value, a function tells us its corresponding y value. So this is how mathematicians create graphs. This is the basic way, or this is the most simplest form of how mathematicians or engineers create those beautiful graphs you guys see on the internet. Especially the Mandelbrot set, which is arguably one of the most beautiful and most elegant graphs in mathematics, and those uses a special type of function called holomorphic functions, which basically map complex numbers onto complex numbers. But that's a topic for another video, and I probably won't be discussing it here, but in origin. So alright, so for any x input here, the function tells us the corresponding y output. So another way to think of a function is, alright, let's say this is a set, and then this is another set. A function sort of corresponds one element here to an element here. So they sort of give a relationship to one element here to another element here. So let's say that this is the set of all femboys, right? And this is the set of all other femboys. A function assigns a map between this and this. So given two femboys, a function gives a relationship, gives them a relationship. So this one likes the other and likewise. So we can think of inverse functions as sort of a mutual understanding or an actual relationship. Wherein when one femboy likes the other femboy likes that femboy. So the regular function is the femboy liking the other femboy, and the femboy returning that or reciprocating that feeling is the inverse, basically. So it's just the reverse of it. So that's the basic concept of a function. So it's f of x is usually shown or defined or syntaxed via a formula, which is called a function rule. Things you guys know or learned in algebra, such as x squared, 2x squared plus 4, cosine of x, sine of x, tangent of x, e to the x, or which we call x of x in higher mathematics, or maybe even summation formula. So f of x equals the sum n greater than 1 of x. This is a function technically, but it's a summation of x for values greater than 1. So that's actually minus 1 over 12 because that's an infinite sum from 1 to infinity. Okay, so that's not the topic. So either way, these are all functions, and they're actually called bijective functions because for any output x, there's a specific output for each x. So no two inputs have the same output. So that's the most basic gist of what the bijective function is. And there are different types of functions, and it's called some of them are called they're very intimidating. The names are kind of intimidating, but once you get the right intuition on what they are, it becomes beautiful. So there's the surjective function, the injective function, the bijective function, and I think there's another one. I kind of forgot it. I don't think it matters in this video. The point is, what a function is, or a map, well, the two terms are usually interchangeably used, is basically a correlation between two sets. So a function gives a sort of relationship between one set and another. So that's what map is. So in higher mathematics, or in more generalized mathematics, such as group theory and category theory, we denote these things or these maps as, we have f of x equals alpha. Alpha maps, let's say this is a set M and this is a set N. Alpha maps N onto N. And this looks a bit intimidating, and you guys saw this in the proof that I did. So we're basically saying that alpha assigns all elements here to all elements here. So it gives the relationship from this set to this set. So we sort of read it literally. So let me just zoom in a little. Okay, read it literally. Alpha maps M onto N. So this M onto N is showed directly via this arrow pointing from N to N to show us that alpha is assigning elements from N to elements of N. So that's the gist of what a map is. And so now, what if instead of sets here, instead of collections of objects here, what if we have groups? What if we want to map G onto another set, another group, let's call it H. So let's let H be another set. So N star, just to show you that it's not the same as the underlying set of G. I'm mapping alpha from G to H is an orbit on G, or rather a left orbit on G onto H, because it goes from G to H. This is the basic form of the orbit, but a more rigorous definition for what an orbit is this. Let G be a set. I mean, a set, not a set, but rather a group. So it has a binary operator. Its elements, or the elements of its underlying group, satisfy the group axioms. And let S be a space. And a space is basically a set equipped with additional structure. So when we say structure, it's mostly in the form of operations. So when we have a set or collection of objects, we usually cannot do anything with those objects. We just say, let this thing be a set, right? Let this be a set, a collection of mathematical objects. But we cannot do anything on the objects as of the present moment because we've only defined it as a set. But once we say that we can perform addition, multiplication, product, anything, any operation on the elements of that set, it immediately becomes a space. This is what we call stuff like our Euclidean space, because we can add stuff, we can divide stuff, we can multiply stuff in it. It has structure. So that's S. Let S be a space. And last one, let T sub S be a transformation transformation of a space. So a set of all transformations we can perform on S. So probably a set of matrices that we can perform on this, with the set of all matrices we can perform to modify the basis of our space S. So set. So I'm just gonna erase that and rewrite it. Set of all transformations on S, the space S. Alright, so the orbit on S, orbits are not really, the formal definition of orbits really depends on the space or what we're really mapping G onto. So it's more defined on S, or the space S. So yeah, we can call mapping between two groups an orbit, but really in essence, orbits are maps between groups and spaces. So I've already showed you guys what that is. Let G be a group, let S be a space, let T of S be a set of all transformations on S. So the orbit on S is defined to be alpha. So that's the function, the mapping, and a function alpha that maps G onto the group composed of the transformations and the binary operator product. So T sub S and dot. So this is a group over here. So this alpha maps G onto this over here. And another formal definition of this is that if we let X be a set, right? A left orbit from G on X, or of G on X, is alpha mapping the product G times X, or G with X, onto the set X. So we take the product first of G and X and sort of map it onto X. That is a left orbit of G on X. And there are a couple of things that an orbit must satisfy, and that is, if we follow the syntax for functions, alpha acting on E and X, or the order pair E and X, gives us X, right? So it's the identity element, and if we interact with the identity element with X, we just essentially get that X. And so this over here is basically just telling us it's commutative, so we can move it out. We can distribute, or so not really distribute, but rather we can factor out, factor out in the most loose sense. And if we can't get things confused, of course, the identity element acting on X is just X. I already discussed what an identity element is in the previous video on groups, or the first episode of these expositions. So that's what an orbit is, and I hope you guys aren't confused about what I talked about or what I said.